Hey, welcome back, everyone. I get the sense a lot of us are like a little lower energy today. That's cool. By the way, does anyone know what the image refers to? Anybody know the term that is being suggested by the image? Rubber duck debugging is correct. So for those, who's anybody heard of rubber duck debugging besides whoever? Cool. So I'm putting it up only to say this is not a good substitute for pair programming. Rubber ducks make much less dynamic pairing partners, but if you're in a situation where your pairing partner is not available, I've actually found some version of this approach to work pretty well. So for those of you who have not heard of rubber duck debugging, the idea is if your code's not doing what you expect, you sit your rubber duck down on the keyboard and you explain to your rubber duck each line of code. And the rationale is that forcing you to verbalize what you think each line of code is supposed to do and what assumptions you're kind of making when you wrote it will often be enough for you to reveal the bug to yourself. And I'm sure you've had the experience of, you ask a friend for help debugging, and as you start explaining what the problem is, you suddenly understand, like the source of the bug is revealed to you. So if you haven't tried rubber duck debugging, try it when your pairing partner is not around. Pairing is still way better, in part because if you're pairing according to the proper protocol, which means that as you're writing code, the person who's driving is explaining and sort of thinking out loud, and the observer is kind of cross-checking everything, that's actually the best version, because then you're likely to catch the bug sooner. Anyway, there we are. So we're going to continue today and next lecture with the theme that we started on Tuesday, which is how to make your code easy for others to modify, or as easy as possible for others to modify. So when we started talking about Agile, we said it's about embracing change and understanding that it's a fact of life, and it's one of the strengths of software, that if you can manage the change process, software has this great property that hardware doesn't have, which is after it's deployed and in the field, you can keep improving it. So the flip side of that is in order to make it tractable for someone else to pick up your code, you do have to go out of your way to make your code easier to understand. And that also includes when you come back to your code in a few months, right? So we took a stab at starting on that on Tuesday. If we think of functions as sort of the basic building blocks that all code is ultimately made of, we looked at these guidelines called SOFA for writing good functions. They're short, they do one thing, they have few arguments, and they stick to a single level of abstraction. So today we're going to try to apply some of that same kind of thinking, but at the level of classes. What does it mean to design a good class? What does it mean to design classes that interact with each other in a graceful way? And graceful in this case means trying to manage or mitigate the cost of future changes or future enhancements to those classes. So we're going to have a total of really 2 full lectures plus then some on design patterns. As most of you know, books and books have been written about them. So obviously we're not going to cover all of design patterns in 2 lectures. But the goal is to get you familiar with the kinds of thinking that go into them and to get you into the mindset where you can see how to apply them in your own code. And design patterns I've always found sort of challenging to teach because it doesn't seem very effective to me to say, OK, here's a laundry list of good things to do. As you're coding, look for opportunities where your patterns match the good things and then use the patterns. In reality, what usually happens is you start writing some code, and at a certain point, the code gets out of control. It gets ugly in very obvious ways. And you know it's getting ugly because things happen like a change that should be simple ends up being complicated, or a change that shouldn't really affect anything outside of a single function ends up having these little ripply changes everywhere else. So sometimes we call those anti-patterns, and it's basically that is your code crying out for help, saying, is there a better way to do this, so that making those changes would not have been so expensive. So we're going to spend a couple of lectures looking at different ways to do that, but now at the level of classes. Actually, the original idea of design patterns doesn't come from software at all. It comes from the field of urban architecture. This book, a classic in the architectural literature called A Pattern Language, was a way of describing tried and true solutions to problems that occur over and over, not necessarily identical, but similar to each other in a particular domain. And in this case, the domain was urban architecture. So the architect, Christopher Alexander, identified over 250 architectural patterns that solve various kinds of problems in how you plan the layout of cities, how do you plan the architectural elements of different kinds of buildings. It doesn't mean that every single building is going to look identical, but that there are certain sort of approaches that once they've discovered to work well, you should try to reuse them. So pattern language is a little bit of a misnomer. It was, pattern language in the context of architecture is really a conceptual vocabulary for tackling these kinds of problems. It's a little bit tricky when we talk about software because when we say language, we tend to mean a formal notation that can be used for programming. So keep in mind when we're talking about design patterns or when you hear people in the context of software talking about pattern languages, they don't usually mean an actual language in the sense of a programming language. What they mean is a collection of related concepts that help you sort of frame an approach to solving a class of problems effectively. And especially in software, the goal, which again comes from architecture, is how do you keep separate the things that might change from the things that probably will stay the same? Because if you isolate the things that might change, that is one way to mitigate the cost of change. So we've already seen some kinds of patterns in software. At the macro scale, we've talked about patterns that make up the way that application architectures fit together. So model view controller is a pattern, right? It talks about components that have specific responsibilities, the interactions among those components, and who does what. But it's not formally modeled in a language. So you might look at an application and say, aha, this application calls for would be a good fit for model view controller. And sure, there's frameworks like Rails and Backbone and so forth that you can take off the shelf that will kind of get you on the right path, right? They'll save you a lot of work. But it's not as if every app that is model view controller is going to be identical. So that gives you the sense of a pattern language. Other architectural patterns we haven't really talked about, but that you've probably seen. Pipe and filter, if you do a Unix command line and you separate things with pipes. Event-based, programs like games or even a web user interface where it sort of spends most of its time waiting for the user to do something, and it's not obvious what the user is going to do next. So the basic structure of the program is how do you respond to those events? If you've tried writing server-side code in Node.js, it kind of looks like that. It spends most of its time waiting for something to happen. And we can have a separate discussion later about why I'm not convinced that that's a good model for server-side programming. Layers, so if you look at the technology stack of software as a service or the networking stack of TCP/IP, the idea is that each layer has certain responsibilities and presents a certain abstraction to the layers above and below it. So a layered architecture would be another example. There's also patterns for computing things. If you look in scientific computing, there's all kinds of formulas and math problems that structurally share a lot of elements. So linear algebra, right? Matrix multiplication, Fourier transforms, things like that. And then the kind of patterns that we're primarily going to be concerned with are what some people in software call the GOF patterns for gang of four, after the group of four authors who in the mid-1990s wrote what is now considered the sort of seminal book on patterns from the software engineering point of view. And they divided the patterns that they identified looking at different software systems into three different kinds that they called structural, behavioral, and creational patterns. So this was the famous design patterns book, Gamma, Helm, Johnson, and Vlasides. And their goal was to really do for software kind of what Alexander did for architecture, to find patterns of the way that classes fit together or that classes do certain things and relate to other classes that came up over and over again in different software projects across a variety of domains. They identified a total of 23 design patterns, which we now call the structural design patterns. And what they're really capturing is the way that objects and classes communicate with each other, right? So kind of think of the same idea as model view controller, only now it's maybe at a finer grained level and will solve subproblems that would happen inside of a model or inside of a controller, for example. And keep in mind, a pattern usually does not mean a particular class. It does not mean that there's a library that just gives you the pattern. There are often libraries or frameworks that will help you, right, in the same sense that Rails will help you create a model view controller app, but the library or framework itself doesn't implement the pattern. It gives you some machinery, if you will, so that when you want to implement something using that pattern, it sort of saves you some of the common work. So think of it more like a blueprint for a design than the actual design itself. I am not going to do the thing that I think some courses try to do, which is actually to go through the 23 patterns in the original book. And by the way, since that book came out, other patterns and patterns that are sort of derivatives of these have also been identified. So a full list of design patterns is probably in the several dozens by now. And I don't think it's very effective to try to just enumerate them and keep your eye on the lookout for when you're supposed to use them. But the approach that we're going to take in this course is a little bit different. We try to show some actual situations that would arise in the kinds of projects that you all are doing, and in particular how, as the code evolves, it will lead you towards an anti-pattern. it will lead you towards a situation where you're doing something and you're making it harder than it needs to be because there's an existing design pattern that would make it easier, and using that as motivation, then we'll identify the patterns that come into play. So of the sort of 23, I guess, on this slide, we will look in detail at maybe half a dozen. And again, the goal is not that you become an expert in using all the patterns. It's to get into the mode of thinking of how those design patterns are intended to work. I mentioned the concept of an anti-pattern, which is code that looks like it probably should follow some design pattern, but it didn't. Most of the time, it's not because the person who wrote it had no idea what they were doing. It's because the code has accumulated over time more features and maybe more technical debt, right? Technical debt being making changes to the code that over the course of time serve to degrade its structure, even if it's still working, and in particular are going to make it harder to make changes to the code in the future. And probably you experience some of these symptoms yourself that will tell you if your code is creeping toward an anti-pattern. Using the terminology of design patterns, people, viscosity is when you know what the right thing to do is to extend your code in a certain way, but it's easier to do a hack than it is to do the right thing. Right? If your code was well factored, it ought to be easier to do the right thing. Immobility. We talk over and over again about the concept of dry. How do you pull out commonly used things and put them into a reusable module, whether that's a function or a class? If you can identify places where things almost seem to be similar, but they're not similar enough that you can pull out the commonality in a clean way, that's immobility, which is related to needless repetition. When things are similar but not exactly the same, you find yourself copy and pasting code and making small changes. That's a red flag. And needless complexity. So you start out designing something, and you're designing not only for the case you're solving now, but for some future case which may or may never occur, and that adds complexity that you may or may not ever use. So those are just a few of the symptoms that are a tip-off that maybe your code is not heading in the direction it should be. And in the early to mid-2000s, Bob Martin, so-called Uncle Bob and one of the co-authors of the Agile Manifesto and the Agile way of thinking about things, actually came up with a framework for what makes a good set of communicating classes. How should responsibilities among classes be parceled out? So what we're going to be exploring is the relationship between these 5 principles that they laid out and some of the design patterns that were identified in the Gang of 4 book. The acronym SOLID is used to refer to these, and we're going to go through these each one at a time, but there are 5 principles: single responsibility, open close, Liskov substitution, Demeter, and I'm going to give you a caveat. Usually the I in SOLID is for the interface segregation principle, and for reasons that will become clear when we discuss that principle, that one is less relevant in dynamic languages like Ruby, but dependency injection, which is super important, we're going to use the I to stand for that as well instead. So injection of dependencies is going to be our I. Right? So over the next couple of lectures, these are what we're going to look at. And again, the approach is going to be, let's show a real-life example of how something could get to the point where one or more of these principles is being violated. And in that case, what are some design patterns that might be able to be applied that would remedy the violation? So that's where we're going. And in terms of comparing this to what we were talking about on Tuesday, in some sense, on Tuesday we were talking about what do you do at the level of individual methods, right? What makes a method good, and what can you measure about it? So we talked about code smells, which are qualitative aspects of code that can be an issue that tip you off that your code has some ugliness. There's also design smells that characterize classes that maybe haven't been set up the right way. In both cases, there are catalogs that will list different kinds of code smells and design smells you can look for, and refactorings that would help you fix them. There are metrics. We talked about assignment branch condition and cyclomatic complexity for measuring functions. We're going to talk about a couple of metrics, including LCOM, lack of cohesion of methods, that are a quantitative tip-off to one of the solid principles being violated. In both cases, there are refactorings that can help fix the structure of the code. We looked at some simple refactorings at the level of a function on Tuesday. So we looked at extracting methods, moving around code within a class. Now we're going to look at refactorings that maybe extract an entire class, or that move code from one class to another to fix some of the problems. And of course, each one has a handy acronym to help you remember it. And I defy you to remember those acronyms by memory, which means if there's an exam, you won't have to remember them by memory. We will give them to you. So what we're going to do is give examples of the solid principles. We're going to go through each one, show what it means, and show the circumstances under which you might find yourself accidentally in violation, and then showing which design patterns could help bring your code back sort of into more compliance or harmony with that principle. It is a non-goal, as usual, for you to remember all the syntax of all the examples. All the examples I'm going to do are on GitHub or in the book or both, but the goal is to understand the big idea of each of the principles so that you can recognize it when you see it.